Okay, everyone, I would say we get started. I would like to welcome everyone to our presentation, Durable and Resilient Retrofits, Solving with Stone Wool Insulation, presented by Rockwool. My name is Andreas Benzing. I'm Executive Director of New York Passive House, and today's event is organized together with Passive House California and New York Passive House. Both states have a similar challenge with existing buildings, which account for a large portion of the energy demand and CO2 emission. We have Local Law 97 here in the city and other legislation in the pipelines in order to reduce greenhouse gas emissions from existing buildings. So it's my pleasure to welcome my colleague from California, Christian Kienapfel.
Good morning. My name is Christian Kienapfel, board member of Passive House California. I would like to welcome all of you for joining this joint event between Passive House New York, Passive House California, and Rockwell. And with this one, I'm handing it off to Jay.
I want to step up and first of all, thank Rockwell for making the effort to put this together, but more importantly, for their sponsorship of Passive House across the United States, well, internationally, but they are a big supporter and a big sponsor of ours. They were the first organization to spread their sponsorship across not only the North American Passive House network, but with Passive House California and with New York Passive House. And they are also the first, this is the first joint webinar that we've had between New York and Passive House California. And we come together very appropriately with Rockwool for that. In California and New York, we very often co-promote workshops or webinars that one or the other is doing. But this one is actually co-sponsored with Rockwell. Rockwell is really growing in California because they're a very appropriate solution for wildfires or wildfire areas and any kind of building fires. They're very fire resistant. And in fact, I think probably the next joint webinar that we have between New York and California will be next spring, and it will be Rockwell again talking about fire safety, which is such an important issue. Today's presentation is on durable and resilient retrofits. Again, retrofits are so important, and the flexibility and the breadth of the Rockwell product line, it makes them a really good partner and very appropriate for that. So welcome again. Thank you to Rockwell, and let me turn it over to Todd Kimmel and Pamela Sadler from Rockwell. They will be taking it from here.
Great. Thank you, Jay. Thank you, Andreas and Christian. And thank you to the community of Passive House enthusiasts that are out there. My name is Todd Kimmel. I think I'm familiar with many of you that are on this call, which is great. And I'm happy to be joined by my colleague, Pamela Sadler. So both Pamela and I serve as architectural support kind of managers for Rockwool in North America. Pamela is based on the West Coast, kind of nice dovetail with Passive House California. And I'm based here in New York City in Brooklyn. I am also a CPHD. I serve on the board for New York Passive House, and I've been a board member for, I think, going on 7 years. So always exciting to be part of this initiative and kind of pushing things forward. And I think very excited here to be talking about retrofit, which is a hot button topic, definitely in New York, but also in California, and it should be globally. Hopefully, we'll start tackling this because a lot of the energy use that's coming out of our building stock are coming from buildings that have already been built and will continue to operate for decades to come. So it's a very critical component of our kind of carbon reduction strategy globally. And we're going to get into some of that as we go here through this program today. It is an AIA-CU, so everyone on the line, if you guys need an AIA credit, we will be able to get you that within the next week or so. It also will qualify for a GBCI credit. So exciting there as well. So if you guys are looking for those types of credits, we can certainly accommodate. Before I go through the learning objectives, this program is part of obviously these two Passive House organizations. I'm going to admit that this isn't a Passive House only presentation. So we are going to get into some case studies. One of the projects that we're going to talk about is a Passive House project. One might approach Passive House, but really the focus here is on retrofit and trying to improve the energy performance of our buildings. And Passive House is kind of on that spectrum for sure. And so we're going to dovetail a lot of the conversations around what we're talking about with retrofit with Passive House. But not everything here is going to be Passive House related. So I just wanted to kind of set that up front. So why are we retrofitting? And kind of we'll dive into understanding where retrofit and renovation fits within our energy conservation strategy, and kind of more broadly explain kind of the building stock, how that contributes to greenhouse gas emissions targets. We will talk a lot about durability and understanding that when we make any shifts or changes to the performance of our buildings, durability needs to come into play, because we don't want to be making modifications, to create long-lasting solutions for our buildings that then compromise their integrity and their capacity to perform over time as well. So building science comes into play. We want to understand how that fits in not only to an exterior energy retrofit, but also an interior retrofit as well. And we're going to talk about both strategies. In fact, of the solutions that we're going to talk about, one will be an overclad solution. One will be a deep energy interior retrofit solution of not, I don't know if it's a historic building, but an old masonry building. And then one is going to be looking at more of an EFIS type overclad as well. So those are the three that we're going to be highlighting here today. But it's not just about energy. Whenever we talk about kind of improving performance of buildings and we're looking at retrofit, there's other things that are really critical considerations that we need to make. Passive survivability is going to be a big one, all right, in terms of understanding the benefits of things like passive house or any sort of thermal improvement, and how that can actually really contribute to the safety and well-being of residents inside, particularly as we're seeing a lot more power outages these days in extreme heat or in extreme cold, and what this could mean for occupants' health and safety. But there's a lot of other considerations we want to make, right? We're trying to reduce the operational energy use of our buildings, but we also want to come into play with embodied carbon of the materials that we're trying to select. Understanding the durability and robustness around fire performance should really be critical. Understanding long-term performance, right? We don't want to have to make these modifications and spend more energy, in another decade to do all this work again. So understanding all of these things kind of come into play as far as considerations. So today's program, obviously, we're going to be talking a lot about stone wool insulation. So these are going to be strategies that don't include foam plastic. And so that's another unique part about this program, is looking at more kind of, we'll call it sustainable, healthy, durable, robust solutions using stone wool. And so I want to kind of just start off by just minimizing any confusion about what stone wool is, because you guys probably hear a lot of terms like mineral fiber, mineral wool, stone wool, obviously slag wool. And so just to kind of start off here, right, mineral fiber is really the overarching generic term for fibrous inorganic substances. And that's going to be kind of then categorized into three groups: fiberglass, which I'm sure many of you are familiar with, more low density, kind of your pink bat. Then you've got mineral wool. And under the mineral subheading, you've got either stone wool or slag wool. So mineral wool is made out of two primary ingredients, which is volcanic stone, rock, and then slag, which is the byproduct of iron ore when you're producing steel. So slag makes up the recycled content. And so when you have a higher percentage of stone versus slag, it's called a stone wool. If you have a higher percentage of slag than stone, then it would be called a slag wool. So both are under the mineral wool segment. We're going to be talking a lot about stone wool here today, just so you guys have an understanding of what that terminology means. And then you've got refractory ceramic fibers, which we're not going to be getting too deep into today. That's more of an industrial type of an application of materials for high temperature, but not really in the built environment for what we're dealing with. So again, just making the product, basalt, slag, you're heating that up to very high temperatures, and as it melts, it's going to kind of go along spindles, not too different from the process of making cotton candy. And then that melt can be spun into either higher density boards or low density bats. And so that's one of the benefits, and particularly as we talked about retrofits and different types of applications, is that stone wool has a tremendous amount of versatility. So unlike other fibrous insulations that can really only be used in low density bat applications, or let's say on the other end of the spectrum, foam plastics, which are traditionally used in very rigid exterior environments, stone wool can kind of cross that spectrum and be used for both the low density as well as high density applications. And that includes low slope roofs, that includes below grade foundations, under slab, exterior wall, things of that nature. All right, so we'll dive into why are we retrofitting? And so this is probably not surprising statistics for anybody on the call, but right, buildings generate nearly 40% of our annual greenhouse gas emissions globally. When we look at cities, whether or not that's New York or Los Angeles or San Francisco, the implications of our buildings on carbon emissions is a lot higher, right? In New York City, I think it's 68% of our carbon emissions are coming from our buildings. 30%, buildings account for 30% of the energy used globally. 50% of energy consumption is, we'll potentially see a rise of 50% energy consumption if we're not taking any action in this existing building stock by 2050. And really the scary statistic is that typically just under 2% of our buildings are being addressed annually when it comes to retrofit. So we really need to start to kind of shift our focus. And it doesn't really make a difference in terms of what climate, right? Building enclosures will play a major role on energy use of buildings, or the energy use of buildings will play a role regardless of which climate it's in. And so that's why, again, we're here talking about California or New York, right? So these are just charts showing energy sources for office buildings. And so the chart on the left is showing more of a cold climate, Canada. The one on the right is showing California office buildings. And we can see here, right, the building enclosure is going to kind of impact space heating, space cooling, as well as ventilation, right? So three key components that are going to kind of impact energy use. And we can see in either one of these cases, whether or not we're talking about California or if we're talking about Canada, we're over 50% or thereabouts in terms of the impact on energy use is coming from heating, cooling, and ventilation, which all tie back to our building enclosure. And so as we look at specific strategies on how to improve performance, right, we have different choices that we can make, right? Minor retrofit options to major retrofit options to deep energy or deep retrofit options. And so just to kind of categorize these, right? So if we try to take a minor approach, it's really just talking about sealing or caulking, maybe using some spray foam to kind of help improve air tightness, look at upgrading lighting systems, nothing too invasive. We can then also maybe make this shift to more of a major retrofit, which is going to have a little bit more of a holistic approach that you can tier. There's going to be some disruption, but maybe not major disruption to occupants in kind of these efforts. And that could include adding insulation where it makes sense, maybe replacing some of our windows and doors, upgrading some of our our heating and cooling systems, making them more efficient, installing low flow faucets, addressing sub-metering, which we're seeing a lot of going on in New York City based on code requirements. And then the real big one is going to be our deep retrofits, which is a much more holistic approach. It's going to be a higher cost initiative. It's going to require more of an overhaul of the building itself. It could potentially require significant reconfiguration of the interior, maybe a displacement of occupants for a period of time. But now we're looking at, addressing the envelope, addressing the walls, the roof, replacing insulation, maybe having to replace cladding, certainly looking at windows, window modifications. From a mechanical perspective, it could be just fully replacing the heating, ventilation, air conditioning systems, and looking at using renewable technology like ground source heat pumps. Regardless of what we're looking at, as we look at these kind of retrofit opportunities, there's a lot of considerations that we're going to be taking into account. I think a lot of us on the call here today are looking at trying to do retrofits right now from an energy use perspective, trying to reduce that energy use, trying to reduce the operational carbon emissions from our buildings, or the operational carbon, and then also looking at the embodied carbon as well from the materials that we're using. Sometimes we're looking at these initiatives from a thermal resiliency standpoint. I mentioned passive survivability, trying to make sure that these buildings can remain safe in power outages and kind of keep occupants safe and healthy if we're having some climate challenges. Sometimes we're just looking at improving the durability and the robustness of our buildings. We see a lot with local law 11, having to do a lot of repointing of our buildings. Maybe there's some initiatives that we can take here to kind of improve that with a retrofit. And again, sometimes it's just about improved occupant comfort. Many of us are kind of enduring lots of uncomfortable interior environments that can be remedied through some level of retrofit. And so retrofitting for enclosure durability. I talked about durability already. Just so we understand, durability is not an intrinsic property of a material, but it's really a function of that material and the environment that it's being used. In fact, some materials can be very durable and robust in, let's say, drier northern climates, but not so great in southern humid climates. So want to understand kind of that climate perspective and what that means from a durability standpoint. And so before I dive into the case studies around retrofit, I think building enclosure control functions are really critical for us to understand whether or not we're looking at new construction or retrofit construction. And so all these considerations are really critical, right? And so here are it's 6 specific control functions that we want to address. Typically, rainwater or water control is going to be number 1. Rain is the most impactful in terms of building degradation over time. And so we want to think about how we navigate that effectively. We'll see rain screens used quite commonly as a really effective way to address moisture management in buildings. And we're kind of looking at that in this section detail here. Air control is really key. If you have air leakage in your buildings, odds are likely you're also losing thermal value because air is bypassing your insulation layer. But with air movement also comes moisture in terms of vapor that can condense within the assemblies. So we want to understand air control. We want to optimize air tightness. Passive house brings air tightness as a major component of performance from a durability standpoint as well as a thermal perspective. Thermal insulation, we're seeing a lot of added insulation. We're trying to get continuity with that insulation, reducing thermal bridging to optimize thermal performance. Vapor control is also important, particularly based on how we're operating the buildings. Do we have natatoriums or libraries or things of that nature? For sure. But if we have some levels of condensation occurring within our walls, which we most likely will, how do we evacuate that moisture and think about the permeance of the components within our assemblies? Fire and smoke obviously can't be overlooked from a safety perspective. We've seen some retrofits globally that have failed because they've optimized other things and not fire performance, which can really be detrimental over time. And so we need to think about that as well. And then slowly but surely, sound is becoming a big part of this. And Passive House really contributes to very acoustically sound environments, which is great. And that can contribute to more kind of healthy living, healthy learning, more stable, mentally stable environments for the occupants of buildings. Looking at OITC, STC, ASTC rated assemblies is really important. And so ultimately the goal here is to find a balance between kind of this improved energy performance without sacrificing durability and resiliency, and also trying to maximize occupant health and comfort. And so I kind of go over the slide quite a bit and programmatically with a lot of my presentations, but when we deal with buildings, particularly historic buildings or buildings that are needing to be retrofit, not all historic, but existing buildings per se, a lot of them aren't built with a lot of air tightness in mind or with much thermal insulation in mind. And so sometimes the benefits of that is that if those buildings get wet, you put the heat on the inside and it dries those buildings out pretty quickly, and it's not trapping moisture within those walls. And so when we start to build more high performance assemblies, whether or not they're using this kind of split insulation strategy or other strategies, maybe just interior insulation, sometimes just exterior insulation, we have to recognize that as we're improving the air tightness and as we're improving the thermal performance of these walls, they're not going to dry out as quickly as they used to, right? We're keeping them, kind of warmer and relatively dry. So if you have leaks, if you have some diffusion challenges, and condensation issues, you want to make sure that you're building in mechanisms to allow those buildings to dry out through natural diffusion. And so understanding the permeance of your air control layers is really critical. Understanding you might not want vapor barriers in certain climates. You might want to allow for drying to the inside or drying to the outside is really critical. And even with the insulations that you're choosing, vapor permeable insulations like stone wool really can help benefit and maximize the moisture performance and the resiliency of those buildings. And so now as it pertains to retrofits, right, we have different options on retrofits. In general, from a building science perspective, an approach to doing an exterior energy retrofit is always going to be more favorable, right? So if you have little or no insulation on an existing building and you put air tightness on the outside and you put all of your thermal insulation on the outside, it starts to reduce the impact that condensation might occur, that you'll have condensation issues within the existing structure of your building. You're putting it all to the outside. And so any sort of moisture challenges are now happening safely on the outside of the building. And so it can help to improve the building durability that way by kind of shielding or protecting the existing building from any sort of climate challenges or moisture issues. But despite those advantages, sometimes it doesn't make sense. And obviously we have historic buildings. We have a lot of buildings in urban environments with lot line issues where you just don't have the opportunity to add insulation to the outside. And in those cases, moving to an interior energy retrofit might be more appropriate. and can be successful. You just need to kind of understand the science around that and really understand how to manage moisture in those types of assemblies. So here, just kind of overviews, interior insulation retrofits. Again, they're going to be more optimal when you have limited lot lines, as I mentioned. You could be kind of generating some concerns around durability with the changing temperature profile and having that risk of condensation again inside your building. So air tightness is always going to be key in terms of managing kind of that vapor movement within the assemblies. And of course, if you're doing an interior retrofit, one major thing to consider is the occupant disturbance, right? You're going to have to get into these apartments or these buildings, these spaces to do the work. If you're doing it on the exterior, again, it's going to reduce that potential for condensation. You still want to optimize air tightness. It's key in either way. But you also want to understand what is the structural integrity of that building, right? That, you know, if you're trying to attach lots of insulation and cladding to the outside of the building, can it sustain that weight? So doing some assessment there is really critical. Obviously, from a combustibility standpoint, you know, we want to understand fire codes, which are becoming, at least in New York, I'm not sure in California, but in New York, it's becoming much more strict on the use of combustibles. So understanding that impact there. But for the most part, you're going to have lower occupant disturbance. You will have some occupant disturbance. You probably have a lot of scaffolding up, but you're not having to displace as many people. All right, so we're going to go through a few of these solutions. The first one we're going to look at is an overclad retrofit. And so, you know, here, just kind of giving an overview of Overclad, you can see this section detail on the right. You know, pretty standard to a lot of new construction here with, like, let's say a rain screen addition, right? You've got, you know, from your assembly side of it, right? Your primary air control is typically added here to the exterior side of the building. And that air barrier is often serving as your water resistive barrier as well. In this case, the thermal control element is going to be the directly fastened, you know, stone wool insulation. It could be semi-rigid or rigid stone wool. You'll be installing it in between clips if you're using a clip and rail type system for the cladding. And then you've got your cladding, and that cladding can be a variety of materials, from, you know, metal panels to fiber cement panels to porcelain. There's an abundant amount of different types of cladding. And those claddings might have different requirements from an attachment perspective. So that all has to be kind of assessed out. The critical considerations here, as I mentioned, is the structural capacity of that existing wall and where are you fastening these components. Can you attach to existing brick, or do you have to go back to the structure, right? Analyzing that. Maximizing thermal performance is going to be a function of that clip system, right? So you want to try to minimize as much thermal bridging as you possibly can to, again, maximize the thermal effectiveness of that insulation. And so there's plenty of systems that we'll go through in terms of how that can be impacted. Detailing around windows and doors, you know, particularly existing ones, can be a real challenge. So that needs to have some additional consideration. And then last but not least, we mentioned fire. So here's a project that I believe was part of an initiative through New York Passive House earlier this year as part of kind of an overview of Local Law 97. But this is a job on the Upper East Side of New York City, 201 East 79th Street. It was a co-op building, and the design architects are Roger Partners, the contractor CM and Associates, and Rawlings Architects was the architecture of record as well. But this was really driven by the owners of this building, who, again, were just tired of dealing with Local Law 11. Their building was constantly under scaffolding and having to deal with the repointing of the brick. For those people that are not familiar with Local Law 11, it's kind of, you know, the kind of assessment of the brick you have to do every few years. But they were having major issues with their brick. Obviously, the masonry was highly deteriorated, and there was no insulation or waterproofing membrane. You know, these are very traditional. There's an abundant amount of these types of buildings in New York City that were built in the 1960s, kind of wedding cake looking buildings. As they were analyzing this, they were originally thinking that they would try to put additional, or, you know, remedy the, you know, remove the existing brick, put new brick on. They understood that, you know, while they couldn't get to passive house levels, or they felt that they weren't going to get to passive house levels, they wanted to improve performance as much as they could. And in New York City, we have Local Law 97 out there as well. And so this was an opportunity for them to really try to reduce the carbon emissions of their buildings, so that they didn't fall in line with any penalties that are going to be forthcoming from that law. And so they wanted to add levels of insulation. They wanted to improve the air tightness. And so this was, you know, all major goals of this initiative. They wanted to obviously improve the internal comfort. A lot of the occupants of these buildings also saw this as a potential means to increase the property value by putting the new skin on the building as well. Many of these units already had recent window upgrades, so windows were not a prime focus for everybody, but there were opportunities for the tenants to upgrade their windows if they wanted to do that during the time of this work. Again, the solution here was to go with this Overclad. They used a porcelain panel as part of this reconstruction. They used roughly 5 inches of stone wool insulation. So that's going to get them roughly an R20, just over an R20, maybe R22 in terms of thermal performance. And so you can see that here. They did add, before they put that insulation on, they did add a fluid applied air and water resistant barrier to optimize the air tightness. They did have to, kind of come up with some unique strategies around the windows to tie that in effectively. But it ended up, it's still ongoing. It's very close to completion, but they're very excited with kind of seeing how that transitions. And so when we get to the kind of cladding attachment concerns that I mentioned, right? So when we put any sort of cladding onto our building, whether or not it's overclad or new construction, we're putting these types of systems in. We want to think about the thermal bridging that go along with these cladding attachments. And so the project that we just referenced, which I'll go back to, used like a clip and rail system to try to minimize that bridging. If you use these types of continuous Z-girts, you're very ineffective, right? You're at best getting 50% efficiency out of that thermal insulation because you have a lot of heat loss through the bridging through these continuous girts. Moving to these types of clip and rail systems, you can make some significant improvements. You can see here on the right, these kind of intermittent clips are not bridging continuously through that insulation layer. They're more periodic. And now you're getting up to 75% effective. In fact, particularly for the retrofit market, if you can go slab to slab on a lot of these connections, you can get to even higher levels of performance, which is what we're starting to see in that kind of 85 to 90% effective range. You can shift away from metal, right? You can move to fiberglass clips, which are much more thermally efficient than steel or aluminum clips. Again, you up to 95% effective. This is actually an image from a passive house building in Hoboken, New Jersey that used 8 inches of semi-rigid stone wool. This was not a retrofit. This was a new build in terms of this image, but it gives you a sense of these types of materials and how they work. Additionally, there's higher density stone wool that actually can transfer the load of the cladding through it back to the structure. And so this minimizes those clips and rails, and kind of the only bridging you have are the point bridges of the fasteners. And so this can get you to even higher levels of performance. So again, lots of options to think about. But the real key thing here with any sort of overclad solution is trying to minimize those thermal bridges of that cladding that you're putting on the outside. And you can see here, these Z-girts are the worst performing. And as you spectrum down and to the right with intermittent clips and with screw through insulation, you're getting much more efficient and effective with that solution. And so speaking of efficiency with kind of minimizing thermal bridging, EIFS has a really great approach to that, right? By minimizing a lot of that bridging. I think many on the call are probably very used to using kind of foam-based EIFS, but might not be familiar with the fact that stone wool EIFS solutions do exist as well. And so particularly when you're trying to target non-combustible assemblies, you can kind of move in this direction. And so for these types of assemblies, as we look at these kind of control functions, your primary air control and water control, similar to the overclad solution, is going to be that membrane that you place on the existing wall. Your thermal control is going to be, in this case, a rigid stone wool insulation that is not going to be just adhesive based. So there, one of the differences here is you're going to need some level of mechanical fixing to support that, and there are thermally efficient, non-conductive fasteners that can help kind of maximize that performance. But that is something that's traditionally used with stone wool solutions that might not be used with foam solutions. And then your cladding is going to be that finished render over the reinforcing mesh, not too different from what you've seen before. So again, with any EIFS systems, right, critical considerations is drainage capacity. So it's, many times you'll see adhesive ribbons to kind of create some level of drainage behind the insulation, or something that will create a geometric drainage cavity behind that board. You want to always think about the superior board quality and long-term durability. So there are specific products that are generated for these types of applications that might not be the same products that you would see used inside walls or even in rain screens. So some of the mineral wool or stone wool, I should say, is very specific to these applications. You'll often see dual density products that across the depth of the board, the density actually changes. So you have a more rigid outer surface to give better kind of performance from a durability standpoint, as well as kind of a flushness standpoint, and then a slightly lower density product that can conform to any irregularities of the surface, to again kind of make sure that you don't have any sort of transparent shifts visible on the face of the building. And then last but not least, fire resistance requirements, understanding kind of the fire performance here. And so this project here that we're going to reference is a passive house building. This is by ERA Architects. This is in Hamilton, Ontario. It's called the Sobel Tower. You know, a much older building, a kind of low income housing building that had a deteriorating envelope. They had no insulation in this building. They found mold and all sorts of hazardous materials when they got to the site. The developer was really wanting to just kind of tear this thing down and start anew. All the systems were at end of life, but ERA really wanted to salvage the building and understood that from an energy perspective, really trying to salvage an existing building is the number one thing, right? They didn't want to lose the carbon that had already been kind of put into the structure. They really wanted to make it better. And so the goal for them and for the owners here was to create an ultra low energy retrofit that would also maintain the operational affordability of the building for the tenants. They wanted to dramatically reduce the greenhouse gas emissions by over 90%. And so the way for them to do that was to follow the Interfit standard, which is the retrofit standard set forth by PHI, the International Passive House Group. And so a focus here was to reduce the thermal bridging, to enhance the indoor thermal comfort. Climate resilience was a really big part of this because they'd had some power outages in the area and they understood the impact, particularly for populations that might be residing in low-income housing, or if you can consider, senior housing, a lot of populations that might not have the same capacity to evacuate a building under these conditions. We want to make sure that those populations are able to stay and shelter in place if there's ever any sort of weather issues. So that was a big part of this initiative. Fire resiliency was a big part. They did not want to use any sort of combustible materials on the exterior here. And they wanted to make sure that they had the ventilation as they needed it. So just a few images of what this looked like. So this is, again, the stone wool solution that they used. It was 6 inches of stone wool with some drainage cavity behind it. You can see here the reinforcing mesh and the base coat that's being applied, but this gives you a sense of, again, this movement towards a stone wool type solution. And so to kind of circle back on the passive survivability aspect of this building, ERA did a little bit of a study here, kind of comparing and contrasting the existing design before they did the retrofit with the proposed design. And so what we're looking at here on this chart is kind of the power outage impact of this building underneath those two conditions. And so the black line is representing, at the bottom here, is representing your outdoor temperature. So this is kind of an assessment that's happening during the winter months in Hamilton, Ontario, as you can imagine. The blue line up top is representing that kind of typical design, or what it was before the retrofit. And then the red line is representing the proposed design of the retrofit. So you can see here on the left-hand side, before we hit this vertical black line, is just under regular operation conditions. And we're using Celsius here because we're in Ontario. So you just have to kind of understand the differential in temperature shift. But once that power outage occurs at this vertical black line, you can see that our blue line drops pretty dramatically, right? And this pink dotted line represents the typical indoor temperature survivability threshold. So once the temperature starts to drop inside below this pink line, it's really unhealthy for the occupants, and they're probably not going to be able to stay there too much longer without some severe impact to their health. And so you can see just in a matter of minutes under that existing design, it was at a point where really the tenants needed to evacuate that building. Whereas with this proposed interfit kind of approach, it went up to roughly 48 hours before you started to kind of have a slight shift underneath that survivability line. But 24 hours or 48 hours in this case could mean a matter of life or death for a lot of people. And so it's really something that you shouldn't shy away from. And, there was a study that was also done during the summer months. And what they identified was the difference here was that the dangerous levels in the summer kept the occupants able to stay in that building for 4 days compared to about a half a day for the typical design. So again, whether or not we're talking about extreme heat or extreme cold, kind of a movement to these energy retrofits is really impactful for the well-being of the individuals that are occupying these buildings. All right, so the last retrofit solution that we're going to be talking about is the interior approach. Some buildings you might not have the option to put insulation on the outside. Again, it could be because you have a landmark building, you have an owner that doesn't want to lose the aesthetic appeal of the existing building they have. You might have some lot line challenges. And so here, again, it's not that you can't do these energy retrofits. You have to be, more careful on how it's being done. And now all of a sudden your insulation and your air tightness needs to really be achieved on the inside. And so in this case, as opposed to the other cases, our primary air control layer is going to actually be happening on the backside of the existing wall. In this case, we're looking at CMU, but you could imagine this being brick. And so now you're applying what we typically would see as a fluid applied air barrier, in many cases, particularly in the New York City climate, something that's going to be vapor permeable. We then come back with a continuous semi-rigid stone wool insulation that helps to decouple the studs, the interior studs, because we want to minimize the bridging of the studs there. We want to maximize that thermal continuity as best we can. There's always going to be floor slabs and some other sort of structural bridging that we're going to potentially have to contend with. But if we can maximize the thermal efficiency from the semi-rigid insulation, that's terrific. And then you've got your vapor control strategy. In this case, we're seeing it sandwiched between this continuous insulation and some additional insulation in the stud cavity. And so in this case, we really want to minimize the moisture in the air that's transferring from the inside to the outside, right? During our heating degree months, particularly in mixed climates or cold climates, we're going to be seeing that vapor move from the inside to the outside. And so we're trying to stop that dead in its tracks at this location. What's great about these smart vapor control layers is that they will allow for some inward drying if needed, right? And so if the RH level or the moisture starts to build up tremendously in the exterior here, there will be some drying to the inside, particularly during those summer months, the cooling months when that might be really required, because it's going to take a long time for this brick to dry out. And you want to make sure that you can do that to the inside in any cases that might require. So again, for the most part, you're stopping the exterior vapor drive, but you're allowing some drying to the inside. And that can really only be optimized if you're using vapor permeable insulation, again, like stone wool. So some of the critical considerations here are, understanding the quality of the brick, which I didn't talk about yet, right? So we want to make sure that the brick can endure this shift. So if you have really old, poor brick, that might be used to like getting wet but then drying out, because again you put the heat on in the inside and it dries that brick out. Any sort of these kind of deeper energy retrofits, you're going to keep that brick cold and it's going to stay cold and wet for a long period of time. And what does that mean to the performance? Can it endure that kind of freezing through the winters? And so some brick can, some brick might not be able to. And so it's always important to kind of analyze that before moving into this kind of deeper energy retrofit. So that's always, kind of doing some core samples can be helpful. Sometimes you'll see if a building has been unoccupied for a long time and the brick still looks good, that means that it has not had heat, and maybe that's a good qualifier that this is going to be a successful opportunity. But it's always still very, very important to kind of analyze that. Understanding the appropriate amount of insulation to manage that freeze thaw potential is really critical. And again, enabling that interior drying is going to be important. And so the example that we're going to use here is a project in Flatbush, Brooklyn. This is 1701 Albemarle Road. And I'll just preface this by saying this is a beautiful historic building. It was not the entire building that underwent the retrofit. Henson Architects, and particularly Jane Sanders, who was involved as the passive house designer in this one, was just addressing one single tenant who really wanted to kind of showcase how unit by unit we can start to affect kind of the impact of buildings on climate change, which is really ambitious. But with local law 97 in mind, when you have tenant turnover, maybe this is an opportunity for these co-op buildings to really kind of look at strategies to improve the performance of their buildings. So this project in particular might not go to the full Interfoot certification, but it was really kind of targeting passive house as the approach. So again, the challenges here were, wanting to improve efficiency, look at sustainable options to do that, improve occupant wellness. They wanted to look at compliance with local law 97 on any of these large buildings. The focus was on, again, adhering to passive house standards, and they didn't want to compromise or risk the historic integrity of the building. So the goal, again, was to improve the thermal performance, improve the air tightness, create kind of a more durable assembly with limited risk. They wanted to and I think they're still in the midst of comparing the pre and the post performance of the assembly, and also analyzing the brick to ensure that like this was going to be done well, and helping to generate a template for this to be adopted. And so you can see on the left-hand side here, this was the pre-retrofit buildup. Just standard brick, looks in pretty good quality. On the right, you can see the addition of 3 inches of semi-rigid stone wool continuously to start. But they, again, here's some better photos of what this looks like. So you can see they used a fluid applied vapor permeable air and water resistant barrier on the inside of the brick, which is going to give you your air tightness. Might also create a nice capillary break for any moisture that might be leaking in from the outside. But then you've got your continuous insulation. They did build up a stud cavity here as well to the inside of their smart vapor control layer. And by doing this, they're also protecting their air and vapor control layer so that this can now serve as an effective service cavity. So if the tenants want to put in some electrical boxes or nail some pictures to the wall, they can do that without feeling like they're breaching their air and vapor control layer, which is great. And so they did add some additional low density batt insulation after these photos were taken into that stud cavity. All right, so I'm probably a little bit over time, but I'm going to hand it over now to my colleague, Pamela Souther, who's going to talk a little bit about some of the additional considerations I mentioned early on. So with carbon emissions in buildings, right, so we're very focused on trying to reduce the operational carbon emissions with these retrofits. But as we improve that with, whether or not passive house or interfit, the piece of the pie from embodied carbon becomes greater, right? So now, we've reduced the operational carbon, and so now embodied carbon becomes kind of a big push.
Stone wool, as Todd has reiterated several times, is very environmentally stable. There's no off-gassing, no blowing agents in the material, and it doesn't provide or promote growth of mold or mildew. It's actually an inert product, non-combustible, and it has about 16 to 40% recycled content, depending upon which of our factories it is produced in. So on the next slide, when you're considering the overall impact of each material for your specific project, it's not always about how high the embodied emissions are of the particular product, but you also have to consider how much of that product is being used in the building. For the most part, your structural elements will have the highest impact on embodied carbon based upon their individual impact and the high volume of that product use. However, next on the scale are facade products, including the insulation. One thing to keep in mind is that insulation is the primary material that helps to reduce the overall energy and operational emissions of a building as a final product. So when we think about insulation and stone wool specifically, in its lifetime, the amount of carbon emissions saved by using insulation significantly outperforms the upfront emissions from its production. With that, not all products perform equally, and the full sustainability profile of the material should really be assessed. Even within the same category of insulation, environmental impacts really differ. So it's important to consider the types of documentation available in the market. An environmental product declaration is the primary document referenced to assess environmental impacts of building materials. However, there's different types of EPDs available. A product-specific type, 3 EPD, provides the greatest transparency and accuracy when calculating GWP impact. It's a third-party created and validated document that allows you to calculate for a specific product rather than a general product category. A specific stone wool continuous insulation board versus a general heavy density board as an example. A product-specific type 3 EPD also has higher weights when it comes to your lead calculations, accounting for a full credit versus an industry-wide EPD that is only accounted for as a half a product credit. When you're looking at the EPD, the transparent, verified, and comparable information about the life cycle environmental impact of products and services is what we're looking at. Different types of the EPDs available within building products are your industry-wide, valued 1/2 of the product for lead credit purposes, product-specific, valued as full product for lead credit purposes, and considerations beyond the GWP necessary for full sustainability benefits, such as ozone depletion, potential product circularity. Insulation materials are always part of the system and should be compared to in situ to compare full sustainability profile. Todd had spoken briefly to some of the poor retrofitting that happened in the past. And of course, here, if you're seeing the slide already, you're looking at the Grenfell Tower tragedy in 2017. There was a huge loss of life in this, and it took a total of 24 hours to control the fire. So here it just really drives home the importance of using non-combustible materials. And we don't see fires like this in the USA predominantly because of our NFPA 285 testing, which was recently updated in 2019 and will be going into effect in 2022 with the new requirements. But I will say one thing, everyone's talking about who is to blame for this tragedy. Well, this building underwent compliancy for fire. The inspections, they did 16 inspections on this facade. And nobody within those 16 inspections noted that the cladding they were using was not approved for tall building structures. So, where does the fault lie? Well, it starts with us and getting the correct design in there, but also the entire system has to pay more attention to these details. So going to our climate change and the cause of significant increase in the frequency and severity of wildfires, first of all, fire is not strictly a WUI concern. I'm in California, and I'm just as concerned with fire in general as I am with the WUI zones. Governor Newsom has proposed regulations that mandate building materials to be both fire resilient and fire hardening for retrofits. So as a state, I think we're becoming more proactive. And whether you're dealing with a severe fire risk zone or a light risk fire zone, both enclosure concerns and defensive strategies should be considered. This is a quick video we're going to do. It basically is going to be a demonstration, and let me get it started for you and I'll walk you through it. So this is a standard wall assembly using foam plastic on the top and comfort board on the bottom. The bottom video is sped up to show a full 30-minute test, while the top video is much slower, showing only 3 minutes. Vinyl is used as the cladding in these assemblies and provides absolutely no fire resistance, and it melts away quickly. Stone wool at the bottom is providing a layer of fire resistance and providing no flame spread whatsoever. The foam plastic basically provided a source of fuel and quickly spread up the firewall and into the attics. We're going to move forward from that one since I have delays on my video as well.
All right. Well, I don't know if everyone can see it, but I mean, basically what this showcases is that in just 3 minutes, the foam-based product, the fire breaches the attic and they have to stop the fire. In 30 minutes, they actually shut down the test with the stone wool because it wasn't kind of moving forward at all. And so this was put together by the UL Fire Service to really analyze kind of the impact of fires, particularly where we're seeing a lot of wildfires, and understanding the cross section of addressing energy code requirements to improve thermal performance of our buildings with the concerns around fire. And so just kind of understanding that there are options out there that can help with fire hardening. Obviously, it's not just the insulation, it's actually how we're designing our buildings and kind of creating some gaps between the building and any sort of combustibles. But the use of materials is really critical to consider as well, not just in California, but that's kind of a paramount area. But we're seeing these kind of wildfires all over.
Yeah,
All right.
and the foam plastic really does provide a source of fuel, and that's why the fire spreads so quickly up the wall and into the attic. The bottom line on that. So again, the stone wool is non-combustible and no smoke, which is really crucial. So each type of insulation contains different properties, and all of them react differently to aging. The consideration of how the insulation will last through the life of the building is an important factor in the long-term performance of the wall assembly. The industry focus on R value has shifted from nominal to effective. Great. So the difference with foam plastic insulations is, as you know, they use blowing agents inside their cells to achieve the R values. So over time, those blowing agents tend to exit out of the insulation and they're replaced by air. As the air replaces the blowing agent, the R value declines and continues to decline over time. So this chart is basically comparing several products. Year one, they're nominal, and then over time, their effective R value. And you can see the decrease, especially in the colder climates with the foam. There's a loss of R value. And you can also note that the stone wool is consistent, very stable. In California, along with 5 other states, I believe, the blowing agent-free regulations went into effect in January, and other states are joining as we speak in 2022. So again, blowing agent-free regulations now have taken effect. So here we have an example of different insulation R values with varying temperatures. You can see each insulation R value will vary as the temperature changes, and the temperature with the insulation is being used does have an impact on the performance of the wall assembly and the thermal efficiency and performance found during the operation. The NRCA has done quite a lot of independent testing on products like polyiso, and rather than use laboratory testing or laboratory predictions to determine the long-term R value, they decided to measure actual samples ranging from 4 months to a couple of years. They tested around 15 to 20 samples, and the results, which are summarized here by the green line on the graph, the R value is on the y-axis and the temperature is on the x-axis. When a product has an R value of 4.2 or 4.6, that is an R value measured at 75 degrees Fahrenheit, which is the standard temperature, which all insulation products are measured. At 75 degrees Fahrenheit, the performance of polyiso was 5.7 per inch, less than the R6 that the predictive testing would have said. These results are very similar to what the NRCA found. So at the same temperature, the high density stone wool insulation roofing product measured about 3.9, which is a very significant difference in thermal performance. Interestingly though, NRCA tested the product at other temperatures, cold as well as warm, and its nominal for R values of insulation increased when it gets colder because air moves more slowly in cold temperature than warm temperatures. Again, in the case of the polyiso, the R value actually declined as it got colder. This occurred because of the blowing agents, and the product not only loses R value over time, it loses R value as it gets colder. And again, we incur drifting, which can be detrimental to the structure itself.
Yeah, I might just add here too. I mean, so, as far as driving product decisions, whether or not you're looking at retrofit or not, for continuous insulation, I think not many of us are concerned too much with how our thermal performance is at 75 degrees Fahrenheit. We're probably more concerned when the temperature drops below freezing. And so, just understanding that when you look at insulation R values, it's not about the nominal R value so much as it is, again, about the effective R value in terms of how the product's being applied. But in this case, what is that R value at 25 degrees Fahrenheit? And you can see that there's many differences here amongst products. So it's just important to kind of encourage this input back from the manufacturers, whether or not it's mineral wool, stone wool, ISO, whomever, to understand kind of how that's performing for your buildings. All right.
Todd, do you want to take it from here?
Yeah, for sure. Thanks, Pamela. And so we're going to wrap up. I know we're probably a little bit over. We want to leave some time for questions, but I think at the end of the day, we're trying to kind of understand all the considerations it takes with retrofits. And when you're looking at durability and resiliency, stone wool kind of hits a lot of buttons, right? So I think we can all attest to that climate change is real and that our existing buildings are huge contributors to GHG emissions. Deep energy retrofits have to be a key part of our strategy in not just cities, but all over to really make a difference. I think cities, you can make a more of an argument in terms of visibly seeing the shift in terms of impact. But it's not just about reducing carbon, right? I think when we look at these buildings and we understand climate change, passive survivability is a huge component here that is oftentimes overlooked. And I think can also be looked at really the argument for why we need to do this and why we need to do this faster. And it's not just passive survivability. That's kind of a natural byproduct of what we're trying to achieve here, right? There's other really critical considerations. We can't overlook the impact that our changes are making to the building itself from a structural standpoint and from a kind of a resilient standpoint. So understanding the materials we're using, the sequence of how those materials are going, understanding that we don't want to have to retrofit again, right? We want to retrofit once. We want to do it right. We want to do it to the passive house level for sure. And then also, right, when it comes to materials, embodied carbon is something we need to be thinking about, but it's not the sole thing that we should focus on, right? Because embodied carbon doesn't take into account things like ozone depletion. It doesn't talk about a material's potential for circularity, which is really going to be key moving forward. It doesn't talk about life safety and fire resilience. And it doesn't talk about the performance of those products over the decades in terms of maintaining long-term R value. So you have to think holistically about all of those things in the approaches that you're taking with retrofit, but also with the products that you're using within these retrofit initiatives. So really want to leave it there and open it up to questions. We do have some content that we want to get through too, that if you guys are interested to learn a little bit more specifically about Rockwell, because now we're ending our CEU, we've got some slides to go through and kind of connecting some dots with some projects and even further elaborating on some of the projects we saw. But I know some of you have hard stops at 1, so I'm going to take a few questions here now, and then we can go through some additional content and take some more questions at the end. I don't know, will that
Todd,
work for you, Andreas?
Sounds good.
Sure. Before we get into some of the questions, could you go back to the stone wool insulation product applications, the types of applications? Just want to point out that this slide is just a great screenshot for you guys to see, but what's missing off of here is basically your 5th facade, the roof. So I just want to let you guys know that stone wool does come in tapered boards down to 0, flute fill, crickets. It really can help you provide fire ratings, even for things like steel columns in garages. There's rated products for that, as well as garage insulation with white facers for reflective light value situations. So if you're looking at trying to use a stone wool product and you don't see it on our website because it's a rabbit hole, just reach out to Todd or myself, depending upon your location. There's a lot of other products out there we can turn you towards. Thanks, Todd.
Yeah, I'm going to try to filter through here. If people want to type into the chat box any questions that they might have, I will start going through this. There might be more than we can really address here. So there's a question here. I can see, can Rockwell be reprocessed back into new product at end of life? Yes, in fact, globally, we're doing that quite a bit in terms of circularity, but the product can be thrown back in the mineral wool hopper and produce new products. So there's a huge statement around that. I would say that just to kind of put things in perspective, in the United States or in Canada, is that we don't have enough manufacturing facilities nearby to make that approach environmentally friendly yet in the US. It would take more energy to get that product back to our factory. But there's ways that from a circularity approach that you can utilize this product so that it's not detrimental or not unable to be removed from a building and then reused in its existing form. So there's opportunities for that as well. But the hope is that the long-term vision here, particularly for these buildings that are hopefully going to last 50 years, is that we will have that process in place domestically to do that. But the capacity is there to use the product at end of life for sure. I'm not sure. I'll defer to Andreas on the availability of this presentation, but I can certainly indicate that we can supply the slide deck here for you guys to take a look at. Sorry, here I don't want to optimize the screen. Does mineral wool insulation reduce noise transference? Yes. So when it comes to acoustics, fibrous insulations can really benefit the acoustic ratings of assemblies, whether or not that's STC or OITC. So it has really good noise reduction coefficients. With acoustics, it's always going to be about the system, so that you have to look at the assemblies and how that kind of takes form. But mineral wool or stone wool insulation can contribute to very high ratings, and we have some really good statistics around that. So we can certainly follow up. There's a question here about what is a smart vapor control barrier. I won't get too deep into that. There's a number of manufacturers that I'm sure are in this community that can address this, but smart vapor control basically means it's a product that has variable vapor transmission at different RH levels. So it for the most part prevents vapor diffusion through it, unless there's a critical point of moisture in the air that requires that vapor to migrate through. So it can be really beneficial in these kind of interior retrofits where you want to kind of just keep that exterior vapor drive out of the wall. But let's say if you have a leak or if you have any sort of major moisture issue in the outside of your assembly, the pores will open up to allow that vapor to migrate through. And so it's kind of this smart kind of idea. And there's a number of manufacturers out there that provide that. I know that they're involved in the passive house community.
Todd, you have a couple of EIFS questions about drainage path at the back, and how do we achieve it?
Yeah, so I just saw that one. So I will admit that I haven't personally been involved in some of our EIFS solutions, and a lot of this is handled through the EIFS manufacturers. But for the knowledge that I've seen is that can be achieved with kind of adhesive ribbons that kind of provide some level of a small gap at the back of the mineral wool. There's also different ways to kind of shape that. I think one of the benefits that you will see with mineral wool versus foam is the fact that it is a drainable product in and of itself. So it's hydrophobic, but if it's under a head of water, the water might get into it, but the water can drain through it. And so there's some value there in terms of it's never going to be trapping the moisture in the way that, if you have a direct applied foam against the wall, but it's still best practice to encourage a drainage cavity on the backside. And we can follow up and kind of connect you with some of the manufacturers of these systems. I know in Canada, Drive It uses these systems quite a bit, and they have solutions for that.
Todd, there's one by Colin who's asking how we would address ceiling fastener penetrations when using exterior insulation on single-family wood frame buildings. So
yeah. So I mean, I guess it depends on where those fasteners are. So I mean, in general, you typically be installing if you've got furring strips or if you've got clips, right? There's usually pressure points and different types of membrane manufacturers that have self-sealing capabilities or might advise on the use of sealants or tapes at those locations. I don't know if that's the specific question. But oftentimes you're going to want to rely on those membrane manufacturers to look at compatibility of kind of creating those pressure seals. There is some research being done by or in the kind of the pipeline by the Rain Screen Association in North America to potentially be looking at really the impact of small penetrations in rain screen assemblies and kind of how much moisture is anticipated to get into structures, and is that detrimental to overall performance, or in terms of maybe even more so the air leakage and what that looks like. But there are ways to seal it and kind of sequence that effectively. But we can always follow up, and I can get you some good information and studies on that as need be.
there's lots of answers is the bottom line.
So there's another. So does internal wall insulation using mineral wool in bathrooms need any special consideration due to high moisture load, or is the diagram presented with a smart PCL 1/3 into the insulation still relevant? So I might take that one offline. It should still be fine when you talk about kind of modifying the continuous versus the insulation in the stud. Really, you're trying to create a layer where the temperature of the continuous area where the vapor barrier is warm enough that it's not going to be too detrimental. It's not going to be cold enough to allow for condensation is the key. So it should be no issue. But some of these details do require a little bit more of a closer look. So we can look at that. I'm going to take a quick break. I'm going to come back to some more questions, but I do want to go through some of the Rockwool stuff. And if you guys, we're going to have our contact information at the end of this. So if you guys need to follow up with us, we can certainly address those questions offline. But hold on just tight. So, just in general, I think many of you are familiar with Rockwool. We are based out of rock, as I mentioned, basalt rock. The benefit of these products, as I'm sure you guys can recognize, is the non-combustibility. There's been a big movement towards non-combustible insulation, but we don't want to forget thermal stability. So we do maintain our R values for the life of the building. We are very water repellent. So, we have hydrophobic binder and some other content, particularly for our exterior grade products that make them very relevant for use in, let's say, open joint rain screen or, roofing or under slab foundation walls. The benefit here is that vapor permeance, which I kind of reiterated throughout the program, is that, we want to make sure we can allow for any sort of condensate moisture to diffuse effectively through these assemblies. And the acoustics is another big thing. Pamela went through all the different applications that we've got. From a sustainability perspective and kind of the Passive House kind of mantra, I think what's really unique here from the Rockwool perspective is our alignment with the 17 Sustainable Development Goals. So we've made a conscious effort as a company to really kind of take this on and address, I think, 11 of these 17. And so we kind of have this mantra globally to kind of address a lot of these sustainability goals. And just to give you a few examples, right? One is around climate action. So we do have a focus to reduce CO2 emission intensity from the production of our products, because it is an energy intense process. We have long-lasting products really that can outweigh the carbon that goes into these products. But even with that, we're moving towards electric cupolas. We have a couple of factories internationally that are electric cupolas. We have our facility in Western Canada that also is electric. We're looking for kind of cleaner sources of fuel. And so this is our mantra. This is kind of what our baseline was in 2015 and kind of where we're trying to go to really make those improvements in embodied energy. And then from operational energy, we're also looking to retrofit a lot of our buildings or pursue kind of almost passive house levels of performance in our facilities themselves. This is a building in Gladbeck, was designed to improve energy efficiency in that building by 80%, really close to the passive house levels. In general, when we talk about Passive House and solutions, we have some really great certified details to support your efforts in Passive House. A lot of the products that you see, at least on the exterior side, for continuous insulation, our cavity rock product, which is an R4.3 per inch, is traditionally used in kind of exterior rain screens. We have a black face product that we released about a year and a half ago for open joint rain screens. It was used on that job at 201 East 79th Street. So if you don't want to see our beautiful brown product in those open joints, we now have a black surface product. But when it comes to a lot of the large scale Passive House buildings, we've been kind of front and center. This is Handel Architects on the Cornell Tech building, where we were utilized in their exterior wall assembly. You can see as it's being hoisted here by Eastern Wall. Mineral wool in general, right? This is a project by ZH Architects in Manhattan. This was I think it took over the largest by height project in the world that was built to the Passive House standard. This is another high-rise project in New York City by Architectonica that went Passive House levels at East 86th Street that also used the cavity rock product behind a porcelain rain screen. I've referenced this project earlier. This was the Candela Lofts project in Hoboken that used a thermally broken clip and 8 inches of our cavity rock product to achieve Passive House levels there. And there's a couple of huge affordable housing buildings that are being constructed right now in New York City. This is the 425 Grand Concourse with Datner Architects that also use cavity rock. And Handel has another enormous by volume. I think this will be the largest Passive House in the world that is also using cavity rock. So it's not just New York City. In Boston, the Winthrop Center here, also by Handel, is going Passive House that's using cavity rock along with some other materials of ours. So cavity rock is a semi-rigid product that requires clips and rails as part of the assemblies, but we also offer, again, a rigid board, which I referenced during our presentation, that has the compressive strength to transfer the cladding loads through it and reduces the thermal loss by using just fasteners. So this is a project in Queens. This is by Think Architecture. It's the Hannah Corona housing project that used the Comfort Board 110 product. I know Magnuson Architects here in the city is also specifying this in a number of their projects. This is their DeKalb Commons project, which is moving forward as we speak. And then before I go back to questions, just, we do have some really great tools for you. Obviously, we can share the content from this presentation. We have some really good Passive House guides and details to offer you. And then last but surely not least, we are now offering complimentary building science services as well to support the design community with, which has become tremendously popular in these retrofit solutions. Because there is concern about moisture within these assemblies, that we can run hygrothermal analysis, we can run WUFI assessments for your project specific details. There is no cost to this. If you want to just, kind of look at specific thermal bridge concerns, we can analyze that as well. We can run effective R-value calculations for you to help meet code requirements and for submissions to DOB. So it's a tremendous resource. And I mean, you guys might have consultants working on this already. We're probably cheaper and faster, and we can act as a good checks and balances for you. But this is a tremendous resource that I definitely suggest you guys check out and utilize when you can. And I think it's ultimately because we recognize insulation is more than just a nominal R value, as we talked about. There's a lot of things to consider when you're implementing thermal insulation in your exterior wall. And we want to be there to kind of service and support you guys in that effort to make sure that you guys are designing resilient and you're designing durable, robust assemblies. So it's a really great service that I'm going to recommend. So I'm now going to open it back up to questions. I still see 160 people on the call, which is awesome because I think we're already 12 minutes beyond, but I'm here to hang out. So I'm happy to answer questions. If people have to jump off, feel free, but I'll try to go through some of these questions. I don't know, Pamela, did you see any questions out there?
Well, I just wanted to let everybody out there know that our building science team has just added an acoustician to it. So if you have any acoustic questions, then we're also providing that as far as now goes. There's one that really struck me that you should address. It's what are the health and safety concerns of using inorganic fiber material that can become airborne during interior applications? So, I mean, that's a no-brainer. Go ahead with that, Todd.
Well, I mean, so there is no VOCs or issues with mineral wool products, and so there's no kind of off gassing. There's no issues with fibers. there's oftentimes people will wear masks or things of that nature because they don't want to kind of get the scratchiness. But from a health and well-being standpoint, the products that we use, certainly on the interior, all meet kind of Green Guard gold requirements. There is, even for the exterior, they'll meet those requirements as well. So, we can provide MSDS kind of sheets to that regard, but there is no concern around the kind of the health and well-being of people interfacing with these materials.
And we do have testing that documents that the weight of the product itself, the particulates, actually does not float in the air. It drops down. So we have testing results that we can provide you on that as well.
There's a question about details. So Rockwell does offer details, and we can follow up, Ozzy, with you on that if you have those questions. But we can get you some good details on that. We can follow up offline on that. I mean, in general, mineral depends on the application and kind of what products you're comparing it to. There's going to be a difference in price. I mean, if you're comparing batt insulation, we're going to be more expensive than batt insulation for sure, but we're also providing higher thermal value, fire performance value, acoustic values. There's a lot of considerations there. When it comes to more kind of comparison with rigid board products, it depends on the rigid products that you're considering. But pound for pound, we tend to be pretty competitive in that marketplace. When it comes to roofing products, we're probably going to be a little bit more on the expensive end. It's often a denser material that you'll need from us, and you might need more of our product to meet the R value requirements. So there's some benefits there that sometimes outweigh all of that. And it's also going to be a function of region and availability. So there's a lot of things that kind of need to kind of go into kind of the pricing differential requests. There's a question about installers needing special training. There is no special training requirements from Rockwell's perspective. We have a lot of great training videos depending on the applications, but there's no kind of certified installer of our insulation. But we can always make recommendations, particularly in the commercial segment, of some of the better installers when it comes to exterior cladding or even interior types of applications.
And Todd, too, not just for the California guests out there, but Rockwell stone wool is the only mineral wool that is CAL FIRE approved for their approved builders material list. And in January, we're actually getting our WUI certification on 4 of our products that are exterior boards. So, when it comes to the fire safety, stone wool by Rockwell is actually a type 4B versus 4A, which simply means that we have a higher melting point and more fire resiliency afforded to it. So that's just a good footnote to put into your knowledge.
With that said, I would say I would like to thank Todd and Pamela and Rockwell for the presentation. It was great. And I would like to thank Jay and Christian as well for partnering on the event. So we could stick around for a couple of more minutes if someone has a direct question to any one of us.
Yeah, we're happy to stick around, but thank you, everybody. Thank you, New York Passive House and Passive House California, for putting this on. And we're proud sponsors of the organizations and your guys' mission, and certainly moving the world to kind of passive house design and construction, not only for existing buildings, but obviously in the retrofit side of it as well. And so we're happy to continue to be part of this initiative for sure.